did her PhD, all her studies in Italy, and then she decided to explore what Europe had to offer. So of course she went, as other famous Italian astronomers, went to Paris.
Yes,
Cassini.
yes.
And then spent some time in Paris, then back to Italy in Padua, and then she thought that France and Italy were not as exciting in terms of lifestyle, compared to Garching, where some people decided not to go. And she invested a lot of her energy in actually using some of her experience at the Far Infrared, because she was also a member of the PAX instrument team in order to get the ALMA regional centers up and running, which she did successfully, both at Munich as well as Garching, as well as using this as an example in other areas across the globe. And then she was punished for that, and she became head of science and faculty.
I can
but she survived through that, and she stepped down from her appointment last year, and this year she's on sabbatical, actually spending time in Greece, up in Thessaloniki, and because of that, it was a great pleasure to also have her visit us for the past few days. And as some of you know, Paola was collaborating with Roman and Tanyo, who Roman was actually spent the last year also working on ALMA data.
He had a very good time in Garching. Yeah. Sure, he can tell us.
We will send him back. Okay, thank you very much, Paola.
Thank you, Vasilis. Thank you for the invitation. I'm very happy to be in Greece. Everybody was asking, "Are you going to Greece? You're going on vacation?" Well, no, actually, I'm trying to do some work at least. So this is not a very close project, so it's still ongoing. So I don't have a wonderful, at least I don't have the final words of what was the goal of this project. So I'm just telling the status. I'm happy to hear any feedback on this. The project started a few years ago, where we submitted several proposals to try to get more data particularly on two clusters, because we looking at the data which were already available at that time, we thought that there were still a lot of missing information from the data that we had, and we want to investigate it more. And this is particularly related to the gas, which is around the central galaxies. And I'm just talking at the concentrates on two clusters where we have more data, but we are working on more than these two objects. So now it's not moving. So why the circumgalactic medium? So we concentrate on the medium which is around the central, either BCG, so the bright central galaxies, or the radio galaxies, and the center of these clusters. Because in the last decades, both simulations and observations have indicated there is a lot of activity in this medium, which surely has an important role for the formation of galaxies and clusters. And we witness inflows and outflows of the gas. So we witness surely connection with the AGN, but also mainly with the star formation. So there are a lot of gas which has been expelled by supernovae. And these conditions are extreme. And what we see still, there are star formation in the outer part of the central galaxy. So, and that's why we would like to investigate whether there are some missing gas, in particular the cold gas, which you know is the site where stars forms, and whether this has a connection to eventually a different way star may form. So indeed, there are evidence. This is one of the last nice ALMA observations taken in atomic carbon. So here, this is a galaxies, a radio galaxies, a redshift almost 4, where you have an extended Lyman Alpha Nebula, and ALMA have seen a stream of neutral gas, the atomic neutral, and which is perpendicular to the radio jet of the galaxy, and which is inflowing into the galaxy. So here you see the spectra at the various positions here. And this is very interesting because it looks like there is a stream going down to the central region, which has a huge mass, because the mass in the stream is almost 10 to the 11 solar masses. And this is just one of the last example of information that we are getting on this type of objects. So what there are indeed the simulations. This is just a parenthesis because I connected this to the formation of stars. So I guess all astronomers know what the initial mass function of stars is. It's the number of stars. So as here is shown as a function of their masses. And for many years, for decades, people have believed that there is a kind of universal initial mass function, and this has been used for computing almost all the, let's say, cosmological models and simulations. However, this is just showing that these are simulations, if you simulate a molecular clouds and you put some turbulence in it, then the resulting initial mass function is different. So it's more skewed toward the formation of high mass stars instead of what is, let's say, taken, which are these two curves, which are usually the Chabrier and the Salpeter. So this is just not because I'm claiming that this is true, it's just I'm claiming this is a possibility, okay? If you change the conditions of molecular clouds, you make change the conditions how star forms. And indeed, there are some evidence of a change in the of the IMF, but this is observations again with ALMA of the ratios between CO13, so the isotope log of the the carbon monoxide, and the CO18, the C18O, which is another carbon monoxide with the isotope of the oxygen, so the 18. And if you compare the ratio of these two, it has been seen that in high redshift objects, some millimeter galaxies, this ratio is much lower than what is seen in the local universe. And this has been claimed as a possibility that we have a different initial mass function, because the production of carbon-13 and the oxygen-18 is different. So one is in low stars and the other one is high mass stars. So, but this is, of course, is a claim. It's not a proven fact, but it's an indication. Other indications coming also from ALMA is the study of the Magellani Clouds, where all these are single, very, very small blobs, where people believe are the cocoon of forming stars. And if you count all these blobs and you sum up and you count the number of possible stars, you end up with the idea that indeed here, if all these become stars, the initial mass function here is also different and is skewed to high mass objects.
May I ask something?
Yes, sure.
The color bar stands for gas density. Because I cannot see from here. What's the color bar in the?
Yeah, this is the gas density. Yes.
Gas density.
And they have identified, let's say, blobs, very, very cold blobs. So it's believed that they were the cocoons of forming stars. So what are the traces then to look for gas and the gas forming stars? Originally and historically, I mean, everybody was looking at the carbon monoxide, because has been seen that carbon monoxide is very well related to the presence of molecular hydrogen. And molecular hydrogen is the most abundant molecules in the universe, which is the origin of the formation of stars. However, it has been seen, and now at least in the last 15 years, that this is a very, yes, it's true, in many cases it's true, but not in all environments. CO traces the molecular hydrogen. And in particular, if you have, it's enough to have a few cosmic rays in the gas, which cosmic rays are easily produced by supernovae, for instance, then the CO destroys. So what happens to the tracer? Let's go the traditional photodissociation region theory, which is the, let's say, a theory that everybody uses when we will try to understand the all the emission lines of ions and atomic and molecules. I mean, this is a theory that's been produced in the 70s and yes, even before, where you have a number of photons produced by stars, by massive stars, and you study how the number of photons is able to dissociate and ionize the various atoms, and for instance, oxygen and carbon, and how much these photons penetrate in the clouds. And you see that the FUV photons, so the far UV photons, are not able to penetrate deep when the clouds is very dense, where the density is very high, and cannot dissociate it more. So that's why the cocoon of the molecular clouds where CO resides is very cold and stay cold. However, if you have high energetic particles like cosmic rays, they are able to penetrate and then destroy the CO. So this is something that we also in the in PDR, the photodissociation region, it was well known. Okay, it was just maybe neglected for a while, and that's why we are trying to find other tracers, and then we are asking ourselves: is the atomic carbon a good traces of the CO for molecular gas? And that's the main driver, let's say, of our investigation at the moment. Also, another very weak point of CO is that this is the conversion factor between the line luminosity, the CO line luminosity, the ground rotovibrational levels of the CO 120 with respect to the amount of the mass of molecular gas, the cold molecular gas, as a function of the metallicity of the galaxy. And this has been clearly seen. I think there is a good consensus now that if you go to low metallicity, the CO doesn't trace well the molecular gas. So it's tracing the molecular gas at a metallicity solar and above solars, but if you go to very low metallicity, this is not any longer the case. So we need to find other traces if we want to study the gases in a low metallicity region. Indeed, there are now, I mean, the last decade, several models and simulations have been produced. I'm just showing a couple of them, and then I go to the observation. So this is a work by Thomas Bispas, and he shows here the CO SLED, which is the CO spectral line energy distribution as a function of the rotovibrational quantum number. So this is usually is a very nice tool to study the physical status of the gas. So here shows the various way cosmic rays, the far UV intensity and metallicity influence this spectral line energy distribution. And if you see, while the FUV intensity doesn't affect much, okay, the different lines is because of these are diffuse clouds and these are dense clouds. The cosmic, even a slight amount of cosmic ray density changes a lot the shape of this. And this is a function of metallicity. There are other models showing this, but why are we looking at the atomic carbon? Because first is an atom, so it's much easier to deal with in terms of physics. The atomic carbon have two fine structure lines in the some millimeter. So it's for some millimeter, it's high frequency. So even ALMA has difficulties in observing these two 490 gigahertz and 809 gigahertz, but still there are receivers to detect it. But a higher redshift is much easier, it's much simpler because these are shifted to lower frequency. So So we are testing whether this really remains a good traces of H2 of them. And since that's much easier to deal with, we are investigating whether it's an alternative and how bright it is, because one of the argument against it, this is not enough bright to be detected in the high redshift universe. However, other simulations shows indeed that if you go, these are hydrodynamical simulations where you have the radiative transfer and you try to see what happens to the various tracers. So you see this is Cc+, so it's the ionized atomic carbon, the neutral atomic carbon, and the carbon monoxide. These are how the simulations produce. And if you see, if you go to very high density of the H2, CO only traces the highest density, while the other tracers are able to retrieve most of the molecular hydrogen. This is, again, is a simulation, so it's not the reality, but at least is what we try to understand what reality should look like. So I just show that. And this is another example showing when the presence of cosmic ray changes deeply the way we measure we're able to retrieve the atomic, the molecular hydrogen with CO. And so these are, again, the molecular gas, the molecular hydrogen for different density of cosmic rays. This is how C+ traces, and this is how CO traces. And if you see with a higher density of cosmic ray in practice, CO is completely dissociated, while C+ and atomic carbon survive. So one of the reasons why we are investigating these tracers. So these are our observations. So we start with a cluster, redshift 0.35, so relative nearby, but it was pretty interesting because it shows a lot of activity in its circumgalactic medium. This is an HST image of the cluster. So the three colors are the three filters, red, blue, and green. And on top of it is the H-alpha emission measure with MUSE at the VLT, and showing that this is the central radio galaxy, the BCG, showing that there is a lot of activities and star formation far away from the BCG. The distance here is more or less 30 kiloparsec, which is pretty far from the central galaxy. And this is the comparison between H-alpha and CO10 and H-alpha CO322, showing that there is indeed, again, in these tails, not only H-alpha, but also molecular gas. So it's very interesting then to look at what is happening there. However, what is happening is pretty different what we see in normal interstellar medium, because these are ALMA observations. These are the dust. So this is a diffuse, so the continuum in band 7, so the continuum at 800 microns, plus the CO322, and on top of H-alpha and nitrogen plus. And if you try to normalize the flux from the central up to here, you see that there is a huge amount of dust. These are the band 7 and 6 of ALMA, which in continuum are showing the emission of the thermal emission of the dust. And these are the CO322 and so on. If you analyze this data carefully, you see not only that you have quite a large amount of molecular gas up there, computed from the CO emission, but you have a very, very cold dust of 10 Kelvin, which is for interstellar medium is pretty cold. It's cold because on top of you have a very excited, a highly excited gas. The ratio between the CO322 and 120 is almost 1. So it means that the gas is pretty excited with respect to the ground level. And indeed, if we look in more detail, we can estimate that there is still star formation rate from H-alpha in this tail. and where there is this very cold dust and excited gas. So this is one of our first target where we have investigated more. And the original idea was to try to see whether we miss gas there. There might be more gas because there is a lot of dust. Usually the gas to dust ratio is something that the astrophysicists consider almost constant, at least in galaxies similar to the Milky Way, so where the metallicity is almost solar. And in galaxies, we see that this gas to dust ratio is pretty low. So instead of being 100, 150, it's of the order of 10 or 25. So our original idea was maybe we are missing the gas. So maybe there is some gas there that we don't see. And one of the reasons could be that since ALMA is an interferometer filters out the diffuse emission, the extended emission, and it might be that we are losing this. That's why we have asked more observations on this with a compact array and with a single dish, with the idea to recover the entire flux. So since ALMA doesn't have the possibility of tuning the receiver at the frequency of the CO76 and the atomic carbon 2 to 1, we had to go to the single dish. These are apex observations of this region here, where you see there is a lot of atomic carbon, even excited, because this is the upper level of the atomic carbon, and see the gas is also excited in CO. However, this ratio is high. The ratio between atomic carbon and CO76 is high, which is already a signature of a gas which is rich in atomic carbon, which might be the presence of the cosmic rays, as I was showing before. We observed also with an Nobeyama 45 meter to get the entire CO1 to 0. And we are working on this data to understand whether really we are missing gas or not. This is again tapering the ALMA data. So these were the original ALMA data. Tapering the ALMA data, you start seeing that there is more diffuse gas. But however, still tapering, of course, cannot retrieve the information that you don't have in the data. So we are working on putting everything together. Now we try to study the physical status of the gas. As I showed you before, one of the tools, one uses the ratio between the lines, the excited lines with respect to the ground level of the CO10. So this is normalized to 10. And these are the 4 data that we have for the circumgalactic medium and for the central galaxy. And so this is, of course, so we have large error bars because the data are what they are, but we are now trying to investigate what this means. If you put this in another way, so this is the line ratios, so the line luminosity ratios, and if you put the flux ratios, you may use several LVG codes which try to give you an output, the number density of the density of the gas and the temperature or the kinetic temperature. However, there is a big degeneracy here because you cannot disentangle the two. So you get a couple of values, which is the electronic density or the density of the gas and the kinetic temperature. However, this is already showing here that for normal, let's say, densities of the gas, or let's say normal, what we usually measure in the interstellar medium, we have a very high kinetic temperature, which is per se already telling us that the kinetic temperature of the gas is much higher than the dust, okay, because we saw the dust here is very cold. And this means a kind of decoupling, a thermal decoupling between the gas and the dust, which is very interesting, okay? And that's a consequence of the formation of star formation. Since we don't have many detailed information yet, what we can do is compare the ratio that we found with what we see in the nearby galaxy, in the nearby universe, and for other high redshift galaxies. So here I show the histograms of the values between the luminosity of the line for the CO76 and the atomic carbon 221 for our objects, and we compare to nearby objects. Nearby objects are here shown in gray. This is the number of objects showing these values of the ratio in the nearby universe, plus these are values of high redshift objects. Some of them are lens galaxies, so they might be that this ratio has affected by differential lensing. So, but the lensing, gravitational lensing may affect different regions in a different way, because the CO76 may be in denser region, while the atomic carbon is more diffuse. So you might have this effect. It's very difficult to retrieve unless you have very high resolution images of everything. But for other, let's say, not lensed galaxy, it's already clear that these values is the values for max is still in the lower range for nearby objects. So this is I put also the values for the Milky Way center, which is very active, as you know, and the outer region of the Milky Way. I will go later on the spider on the green value later. This is similar, and a similar plot to investigate the ratio between the 7.6 and the 1.0 of the atomic carbon. The data are much less because this CO, the ground level of the CO is very difficult to observe for high redshift objects. And so we don't have many data, but okay, so this is very scanty information, but showing indeed that these values are pretty peculiar for the CGM and max, and requires more investigation on this. So what can we do with the data that we have? We can estimate the amount of molecular gas with their atomic carbon value. So we have a luminosity of the carbon line, and we can use this luminosity to convert it to a mass of the molecular gas, which this is the values in solar masses that we find, so around 10 to the 10th. The uncertainty is due to the fact that the kinetic temperatures I was showing before has a big range of uncertainties because of the large error bars in practice. However, you can do the other way around, estimate the molecular gas with the CO and try to infer the abundance of carbon, which is also interesting, okay, in the CGM, in the circumgalactic, how much carbon exists. And this is the carbon produced by stars. So it's okay, this is just was an exercise. We are still working on this data, so I cannot conclude it, the paper on this. However, we shift the attention to higher redshift. The idea was to have a sample of clusters at different redshift to make a comparison in kind of evolution. This is a well-studied protocluster, which is called the spiderweb, because it has a kind of, if you see in the HST image, you see a kind of spiderweb there, at least what the astronomers saw here. And what is very, very interesting, this is a well-studied, so we have a lot of information. It has been shown, this is again the same objects, observing other wavelengths. So these are radio observations. So the point here in red or pink, and this diffuse pink values, pinker gas is what we see in Lyman alpha. And what is very interesting here, there's also all this blue gas has been seen with ALMA and has been seen exploiting this the Dovich effect. And so the people have combined, so this people, Dimascolo and al. They have combined the data from ALMA, from the compact array and the large array, and with the X-ray emission of the gas, and they show here the gas which has a decrement. So you see a dip in the ALMA data, which is related to the Compton effect, the inverse Compton effect of the hot gas in the galaxy. It is very interesting, you see, because you see something that you don't see at any other wavelengths. And the idea for us is to investigate that part of the gas as well. So what we can do with our instruments. So up here we have single dish data of this cluster, and in C+, so in the ionized carbon and the CO10 that you see still at the very large, away from the radio galaxy, there are still cold gas and excited gas. So this was one of the critical information, and with a large mass. And this is again the same gas, but seen in CO43, so it's excited, and the ground emission of the atomic carbon. This the first ALMA data that we were exploring were the central radio galaxies. So these are in the CO423, so is this line, and atomic carbon 120. However, if you take out only the rest of the gas, you take out only the central region of the gas, we have here the atomic carbon, the ground level of the atomic carbon and the excited level of the atomic carbon, and you can study the central radio galaxies on its own, as we have done. And this is, again, the central emission, but seen in continuum. And when you see continuum, you see also some of the extension of the gas outside the radio galaxy. So if you try to put everything try to interpret the physical status, the excitation analysis of the radio galaxies and its medium around it, here I plot the ratio, the line ratio between CO423 and the atomic carbon 10 against the 423 and the CO10. And these are compared with nearby galaxies in green, and the red points are higher redshift galaxies, and the values for the CGM, for the circumgalactic medium, and the radio galaxies in the spiderweb are pretty distant from the rest, okay? And combine this with another excitation analysis against comparing the atomic carbon and CO10 and the CO13 to the 110, you see again that with respect to the nearby objects, at least both values are a bit higher than the rest. So I'll go back to this. And if you go to the central galaxy, to the radio galaxy, here is shown the various lines observed, the CO10, the 423, the atomic carbon 120, and the atomic carbon 221. So you see there is a large component of atomic carbon here in these objects, which was pretty amazing, okay? Because we were all expecting that this gas it's not bright. So and indeed, what we are seeing in many objects, this is just an example that we are looking at, is this atomic carbon is more and more is brighter than we thought. So the power of this analysis is very interesting because we can combine the ratio of the atomic carbon, so the two lines, giving us the excitation temperature, and we combine this with the spectral line energy distribution of the CO that I showed you at the beginning of the talk. And here you try to at least constrain the values of the physical quantities of the gas. If you put the value of the ratio of the atomic carbon to 1 and 1 to 0, which depends on the kinetic temperature and the density, on the density of the gas, and the CO sleds Okay, and combining the two, you can constrain at least the kinetic temperature of the gas and the density of the gas. And this is a very powerful tool which has not been exploited much until now, basically because of lack of the observations, because you need well-sampled COs, LEDs, and both the lines of the atomic carbon. But it's at least we can start doing this in a few objects. And if you combine this information, here is shown the ratio of the two carbon lines against the dust temperature. And you see that for many objects which are considered some millimeter galaxies, okay, you see that this there is a kind of decoupling between the dust temperature and the excitation temperature, so the kinetic temperature of the atomic carbon. And this is very interesting results because it shows how there might be a thermal decoupling between gas and dust. So the gas is, so I show you first the various curve here. The upper curve here is the local thermodynamic equilibrium. All the lines below are not in local thermal equilibrium. All the astronomers usually use the LTE conditions because it's much simpler to solve the equations. However, this plot shows clearly that we cannot apply this condition to this gas, and we have to have more information to disentangle the physical quantity of this gas. So this is still results taken on several some-millimeter galaxies, showing an interesting effect which needs to be investigated further. So we went on studying these objects, and we wanted studying the circumgalactic medium. We found a way to subtract the central sources of the spiderweb. And these are the images resulting from the subtraction of the central sources. The subtraction of the central sources has been quite cumbersome, but at the end, the show is, since the dynamical range of the images been reduced, you end up discovering other not only you infer the gas around the galaxy, the central galaxy, but you find also other gas blobs. And we are still investigating this, so we don't know exactly what it is, but here I show the subtraction of the central source. It is emission of the central source in CO423, and this is the residual gas once we subtracted the central sources for both lines that we are investigating now. And if you do the spectrum of the blobs that I showed you just before, you see this one is at the same velocity as the central galaxy. So this is the spectrum of the CO423 for the blobs that you saw in the southern part, is at exactly the same velocity, while this one is not well sampled, is at the edge of the spectral window, so we cannot infer completely the entire emission, the line luminosity, and this displaces as blue shifted with respect to the central gas. So this is also interesting to investigate. I don't know exactly what it's meaning, because this is just data reduced a few weeks ago. And I would like to go to the conclusion. I hope I make it clear that we are still investigating the circumgalactic medium of these two clusters. The environments in these two objects are pretty extreme, because as I show you, there is a very cold dust and excited gas, which seems to be decoupled, and we are trying to understand what are the consequences of this for star formation. The gas is much excited, much higher excitation with respect to the interstellar medium of nearby objects. So this means that there are other energy sources with respect to the usual far UV sources, which are produced by massive stars. And one of the culprits might be cosmic rays produced by star formations, but other might be X-rays produced by AGN, or some turbulence may contribute to excite the gas. Also, I hope I convince you that the simultaneous use of the atomic carbon luminosity ratio and the CO, spectral line energy distribution, offers a unique tool to derive the physical condition of the gas. Until now, the astronomers have only derived this in a very degenerative wave. So this is a way to break the degeneracy and to disentangle the density and the kinetic temperature. However, if you add also information on the dust temperature taken from the photometry, you have a unique way to constrain a unique picture of the emission of the objects. So as I show you, we are still working on this data and discovering maybe other blobs or other potential gas falling or not falling towards the center of the gas. So I stop here, and if you have questions, please ask me. So any questions?
A question about neutral carbon as a gas tracer. Do you think that there will be, apart from the models, right, that you clearly show that some cases, some environments, low metallicity environments, neutral carbon is able to, at least morphologically, I don't know about the details in intensity, right, to produce the to map H2 much better. But in terms of from the observational standpoint, I always find that much more challenging, right? Because most of the times neutral carbon is calibrated based on is anchored to CO observations, right? Because there is no other way of measuring molecular gas, right? CO was calibrated originally based on observations of molecular clouds that were rotating, and you would get a dynamical mass.
And the AV, yes.
So, but C1, there is nothing like that. So in the literature, you see a lot of people using XC1 conversion factors that are, if you go into the details, they always are associated to CO observations.
Yes.
So
yes.
Do you think there is?
Yes, there is a way. Yes, to disentangle. Yeah, yes. Because if you see this is the mass of the atomic carbon. You see, depends mainly on the ratio, on the abundance of carbon. So if we have a way to determine the abundance of carbon in the gas that we are looking at, then we determine exactly the mass of the atomic carbon without making any assumption on the CO.
Is that equation derived from what assumptions?
Nothing. It's physics. It's just physics. It's just the two fine structures line. Nothing. It's just physics. This is the Einstein equation. The Einstein, sorry, the coefficient exactly. And this is the excitation of coming out from the Boltzmann equation of the excitation of the gas. It's well proven, so it's not something that I did.
Yeah,
okay.
Sure. But that's the key, no? The X C1
yes, this is key.
What brings you from C1 to H2.
This is the abundance of carbon related to the atomic hydrogen. Yes, yes. This is how we determine all the abundance of the elements in the universe.
But
yes,
that is what we want, right? In the end.
Yes, but this can be deduced in other traces. But I agree, but this is the only parameter which prevents us to have a good way to measure them. So this is one, and the other one was at the very beginning, all the criticism came up because this is not bright enough, you will never see. But no, it's not true. We are seeing more and more atomic carbons and C+, so which is still is seen everywhere. You've seen also a very high redshift, right? The C+ is very powerful too. It's a coolant of the interstellar medium. It's more tricky to interpret because comes from different phases of the gas, from the warm, from the cold. So you cannot say, well, C+ is tracing the molecular mass, while atomic carbon, yes, it's just one-to-one correspondence. You had
another question.
Yeah. Maybe she can.
Yeah, okay. I'm gonna ask them on basic.
Yeah.
Do you see any purpose on investigating other molecules apart from C1, such as HCO+, HCl, which are supposed to be very good dense gas traces?
Yes, there are many molecules, and indeed there are many ways to combine observation. However, dense molecules like HCN, they are not so abundant as CO, for instance. So you see, okay, so it's much more difficult to detect them and to derive the luminosity and so on. So we have still only few objects having and they trace only very dense states. So it's a very biased view of the interstellar medium. This is much more diffuse, so you see much more of the entire.
At least the dense cores.
The dense cores, yes, of course, yes. Yes, there are investigations, but I say the abundance is not very high, so the line luminosity is not large, and so we don't have many objects. So the statistic is still poor on those. Yeah. But yes, true, you're right. We have a huge.
I don't know if this kind of data is available, or I don't know.
Well, yes, it is available, not for these particular two objects, because unfortunately we have receivers only observers in different at a given frequency, so you cannot observe all galaxies at all in all molecules or in all atomic ions. So yes, yeah, unfortunately.
Another question.
I have an ignorant question about ALMA.
Yes.
So yeah, I understand that C+ is very difficult to observe because of telluric lines, right?
Yes, yes.
Is it? But clearly you can observe it for with ALMA for high-redshift
Yes.
galaxies. This is because it's redshifted.
Yes,
or?
because it's redshift.
So
yes.
above which redshift can you observe C+?
So it's 158 micron, the laboratory emission. And so from the ground, this is completely absorbed by the atmosphere. So it started being important up from redshift 2 and above.
2, okay.
Yeah,
Thank you.
because ALMA has a higher frequency receivers, which is around 800 gigahertz. So, and 158 microns is 1,800 gigahertz, so 1.8 terahertz. So it's starting shifting in that band. Yeah, but it's difficult because it's high frequency and the atmosphere still prevents good observations. So.
In one of the sources that you showed, it was very interesting when you were showing the profiles of the band 6, band 7, and then CO.
You mean
that one? Yes, that one.
Yeah, here, yes.
Yes. What surprised me a bit is the change in the dust ratios, right? because
Yeah.
there is should be almost the Rayleigh Jeans
Yes,
day.
yes.
So what's going on? There?
Exactly.
What is-
I don't know what is going on. Yes, it's true. It's the question which brought us to investigate this cluster further. Yeah.
Okay.
The ratio of these two bands is pretty large, and so it means that it's
It changes around.
changes.
Okay, so if there are no more questions, let's thank Spot again.